So let's talk about a distribution that is not bell curve shaped. So let's now talk about estimating the mean price of premium diamonds. So here is this, in the pink is again the actual data, that's that 13,000 diamonds that we have in our data set. And the blue is again an overlay of a normal distribution. And obviously it doesn't fit great here, right? This is a very right-skewed distribution. We have many small values and then some number of large values. And so we can still push this data into t_test, and we can say, please calculate for me a confidence interval. And here it is. We might say, I am 95% confident that the mean price of premium diamonds is between about $4,500 and $4,600. So let me ask you, do you trust that confidence interval? Do you feel like that confidence interval accurately reflects a reasonable range of guesses for the mean? If you've fallen into a trap here, I did it on purpose, I trapped you, although I did give you quite a few hints. You absolutely can trust that confidence interval. We have the central limit theorem. I don't care that my data is skewed. I don't care that my data doesn't follow a bell curve. The sample mean of that data is approximately t-distributed, especially because I have 14,000 samples, so I don't even have to worry about that rule of thumb 15 cutoff. And so because of the central limit theorem, if you are trying to estimate a sample mean, a t-test or a t-distribution is almost always appropriate. It is okay to use that t_test or a similar function to get a confidence interval if you are interested in the sample mean. Where our problem comes for today is in the situation where maybe the mean is not the best choice for measuring the center of that distribution. So in this case, we have a very skewed distribution, and that skew pulls the mean to the right. This is kind of like our example from earlier with incomes in the US. Jeff Bezos makes it look like our income, on average in the US, is higher than it is for a typical person. And so a better measure of center in these skewed situations is considered to be the median. So you might want to say, look, I don't care about a reasonable range of guesses for the mean, because I don't care about the true mean. That's not informative. What I'm interested in here is the true median. Of all the universe of premium diamonds, what is the median price? But how would you make a confidence interval for that? Because the central limit theorem doesn't apply very directly to the median. I'm being a little bit unfair here because there's some fancy math and some ways that you can kind of make it work. But technically, for our purposes, you can't just assume the t-distribution for the median. So what are you going to do? What we're going to do is we're going to pull ourselves up by our bootstraps. We're going to use a method called bootstrapping. So here's how this works. The idea is, if we had many, many different samples, all of size 14,000, what we could do is we could just find the median of each of those different samples. And this might give us a reasonable range of guesses, right? We'd see one sample median in one of our sample sets, a different sample median in one of our different sample sets, and so on. And so we could kind of come up with a reasonable range that way. But we don't. We don't have a whole bunch of samples. We only have one sample. So what are we going to do? Well, we can kind of say to ourselves, look, a large enough representative sample from a population. So if the sample is taken in a good way from the population you're interested in. That kind of looks like a population itself. That kind of looks like maybe it's a good approximation for the whole population, especially if it's a big sample. So what if we just resample from our sample? This is a really cool idea. I love bootstrapping because it feels like cheating. It feels like I only have one sample and then suddenly I magically have many samples. But it works, it's great, it's interesting, and we're going to learn how to do it in R. So here's a way that you would take one resampling of the data. I'm going to take these diamonds, I'm going to pipe them into the sample n function. I might ask you, why did I choose to take a sample of size 13,791? And I am guessing that in your mind, speaking to my computer, you got it right. That's because our original data set had that many samples. By convention, when you're bootstrapping, you take your resamples to be the same size as the original sample. So then I might ask you, why have I added this replace equals true argument to the sample end function? Think about that for a minute. What would happen if I did not sample with replacement? If every time I reached my hand in the bag, pulled out a number, and wrote it down, I did not put that number back in the bag? What would happen is my resample would be exactly the same as my original sample. I would waste a heck of a lot of time pulling each number out of the bag and writing it down, 14,000 numbers, and in the end what I've done is I've just written down all the numbers from my sample again. But if I use replace equals true, then I pull out a number, I write it down, and I put it back in the hat. And so that means that some of our observations might get sampled more than once. So here's that resampling, and we can see here we have a new data frame, and we have some prices of premium diamonds, $4,000, $1,600, $7,400, and so on. And maybe I can count up how many times each of those unique numbers appears in this data set. So here I'm going to count up the values that I got in my resampling. And we can see here that this price, 776, was sampled 58 times. And 802, that was sampled 52 times. And so those values, they're being put back in the hat and drawn, and put back in the hat and drawn. And this is where it comes about that these resamplings don't look exactly the same as your original sample. They're kind of like a whole new different sample. And so what can we do? Well, we do this multiple times, right? We said, well, I know what I'd do if I had many different samples. Now I've made a way for us to have many different samples. And so what we could do is do a resampling and look at its median, and then generate another sample and look at the median of that one. And each of these times you run this code, you can see these two code chunks are exactly identical. But because they use some randomization, they use this sample end function, they're going to come up with a slightly different resampling every time you run it. And so in this resampling, the median price was $3,276. And in this resampling, the median price was $3,292. Not quite the same number. And so you can imagine doing this many times, and now you have many different medians, and then you have a sense of the variability in the median. You have a sense of a reasonable range of guesses. So all we have to do now, right, if we want a whole bunch of different medians, is just copy-paste that same code and rerun it several times, right? Great. You would really love to sit here and copy-paste this code chunk, say 1,000 times? Probably not. So the package called modelr is to the rescue. This is, I think, the easiest and cleanest way to do some bootstrapping. And the main function we're going to use, of course, is called bootstrap. And this function just takes many resamplings for you. Be a little careful here because there are bootstrap functions, it's a common name for obvious reasons, in many packages. So the one we want to use today is in the modelr package. A specific package you might have loaded is broom that also has a kind of older bootstrap function that's a little different. So if you want to be extra sure, you can use that double colon trick to say, I really want the function from the modelr package. So here what I've done is I've said, let me take my diamonds dataset, and let me pipe it into Bootstrap, and then I will tell it I would like 100 resamplings. And now let's just look at the first 6 of those. Here we have a data frame, a tibble. I've named it my boots, and it has 2 columns. One of the columns is kind of straightforward. It's called ID, it's a character column, and it's got labels for each of those resamplings. But this strap column is a bit weird. It is a variable where each element seems to have the type list. And each of those lists, instead of seeing them, we're just seeing, hey, this has the type resample. We haven't heard about that before. So let's take a closer look. I want to warn you if you're following along right now, bootstrapping is a little computationally intense because you imagine you're drawing 14,000 numbers out of a hat every single bootstrap that you do. And so if you're trying this on your computer, I would suggest starting with a smaller number. Don't start with 100 bootstraps. Start with maybe 10, or maybe start with a smaller data set as well, and work your way up. So let's look at that object in the my boots, in the strap column of my boots. So if I take just the first one of those, whatever those weird list resample objects are, and look at the structure, this looks like a lot, but I hope you're getting used to looking at these types of outputs by now. So I'm seeing that I have a list. I'm seeing the first element of the list is called data, and it looks like it's just the data set. And I'm seeing the second element of the list is called index, and it's got some numbers. It's got a integer vector. And I can see down here that this object has the object class or object type of resample. So this is not an integer object. This is not a list object, although it is a type of list. This is a resample object. And in this object, we have data, and that data is not actually the original data set. That data element is a pointer to the original data set. And then we have this index variable, idx, which is the vector of the resampled indices. The first number I pulled was number 52, not a price of 52, but the 52nd row. Why do they do it that way? Well, it's because if you imagine trying to resample the data set and save a copy, you're going to end up at the end of the day with 100 full data sets. And that's hard, that takes a lot of storage. But if you just want 100 vectors of indices, that's kind of easy, that doesn't take much storage. So what we do with this bootstrap function to make things more efficient is we really just store the indices of the resampling. And so then you say, well, I actually want to work with the data though. The point of my resampling was to do something with those observations. If you use that data.frame function, then it knows how to convert these objects. So it can automatically take, say, that first resample object that's in our current myBoots data frame, and we say, please give me back the corresponding resampled data frame. And then it knows what to do. It gives you something that looks a lot like the original data, but this one is the resampled version. These are not the exact original values in order. So that's those weird objects, and if you can wrap your head around that strange object, then this is a really easy structure to use. So really all we're interested in here, right, is we're interested in the median price. That's the thing we're trying to estimate, or we're trying to get a range of guesses for. So now we have our 100 resamplings. Let's just calculate the median for each resampling. So I'm going to say, let me map through all of my resamplings. I would like as output to have a numeric vector. And what am I going to do with each resampling? Well, first I'm going to do that trick to turn it into a data frame. And in this case, I'm interested in the price column, so I'm going to look at the price variable. And I'm going to find the median of that price variable. And so here are my 100 different medians from those 100 resamplings. They're similar, right, but they're not identical. And now I can make some inference or make some claims about reasonable guesses based on what I'm seeing here from my resamplings. And actually a thing that I think is even nicer is if instead of just making that vector of medians, if you tack it onto your data frame. So all I'm doing is putting the same code here but inside of mutate, and so now I've got my resampling, the label that says this is resampling number 1, and the median of that particular resampling, the median price specifically of that resampling. So once I have that information, now I can kind of look at what it means. If I were to plot just one of the resamplings, so this is the prices from the first resampling, this is not interesting. This looks almost identical to our original data. It's not perfectly identical because some of the values might have happened twice and some not at all, but it's similar. We've still got that skew. We don't really know much about the median. Here's the median of this one resampling. What is interesting here is the set of all the medians. So this is a histogram of my 100 sample medians. And now this is where I'm going to get my reasonable range of guesses. This is where I'm going to say, okay, what is kind of the middle 95% range of medians of a sample? So we could kind of put those two plots on top of each other. We can see here's my original data, it's quite skewed, and here is my range of sample medians. And it mostly landed around the median of this particular original sample. So what is a reasonable range of guesses? Well, where did our bootstrap medians fall? What happened? The middle 95% of our bootstrapped medians fell between about 3,058 and 3,353. This is a 95% bootstrapped confidence interval for the true median price of premium diamonds. Here's a picture. Oops, giving me a warning. I was lazy about my bin width, but here we go. Here are all those bootstrapped medians, the histogram of them anyway. And here these orange lines are the cutoffs that we just found. So 2.5, well, I guess it'd be 3 of the medians fell below this line, 3 of them fell above this line. Most of what we saw from our resamplings landed in the zone between the orange goalposts. So I'm going to ask you to try this out. There are a lot of concepts in there. Take it piece by piece. Let's look at the MT cars data set, which is much smaller than this diamonds one, so I won't crash your computer. Let's study the horsepower of cars, the HP variable. I would like a 95% confidence interval for 3 different statistics here. I want a reasonable range of guesses for the true mean horsepower, the true median horsepower, and the true variance now of horsepower. And I want to give you a couple tips. One of them is, I would suggest trying to find the confidence interval of the mean using the 2 different methods. First use the t-test method, then use the bootstrap method. See how they stack up, see how they compare. My second piece of advice is that I suggest that you don't redo the bootstraps for each of these statistics. Once you've done the bootstrapping, you have, say, 100 or however many you want, you can do more than 100, you have that many resamplings. And you don't need to do another set of resamplings to calculate the variance. You can calculate the median of each sample, and the variance of each sample, and the mean of each sample, and the whatever the heck you want of each sample without doing another resampling. So I'll end here. I'll leave you to try this out, and most of your practice will be on the lab this week, and I will see you next time.